lovely people working through bivariate statistics. This is for HL and SL. The content here is the same. You can see the points SL content out of our course guide that shows us that we're dealing with the same material. A lot of this you'll have seen before or have at least thought about and used once or twice. There's a little extra bit at the end which is something interesting that we will talk about. First of all, correlation refers to the relationship or association between two numerical variables. We've heard of correlation before. We know about a positive correlation generally going upwards and negative correlation. And for points which are randomly scattered and there's no real pattern, there is no correlation. We talk about whether the correlation is linear or described in some other way. This is a linear one on the left, straight line. Non-linear, still quite correlated those points, but it's clearly not following a linear pattern. The strength of a correlation, strong, moderate, or weak, depending on how closely the points follow the line that you're saying is the line that fits the data the best. And again, we can have a strong positive, strong negative, moderate positive, moderate negative, weak positive, weak negative. We get the idea. Outliers will sometimes exist. This particular point down here, even though it's well away from the other points, isn't an outlier because it fits the trend quite well. The point labelled outlier clearly is an outlier because it does not fit the trend shown by the other points. We can't just throw out outliers and ignore them. We have to consider why they may be an outlier. If it's clearly because there was an error made in recording the data or whatever, yep, you made an error, you get rid of it. If it's just a real piece of data, then we'll have to keep it there and explain why it's different from the others. We can't just throw it out because it doesn't fit. Last thing we need to really remember when we're doing causation, and again I'm going pretty quickly because I think we know this fairly well, correlation does not imply causation. For example, arm length and running speed of a sample of children were measured and a strong positive correlation was found between the variables. Okay, there's a made-up example. Another one, the number of television sets being sold in London and the number of stray dogs collected in Boston were recorded over several years, and there's a strong positive correlation. Okay, these two are made-up examples, but you get the idea that just because a child has long arms doesn't necessarily mean that it's causing them to run faster. People losing or buying television sets in London are not causing stray dogs in Boston. Correlation does not imply causation. And if we jump over to our Spurious Correlations website, oh, why is it trying to reopen it again? We've already got it here. You can see some really interesting examples of things that are highly correlated, but clearly one is not causing the other. For instance, suicides by hanging, strangulation, and suffocation correlates really highly with US spending on science, space, and technology. No suggestion that this is going to be causing the other. Number of people who drowned by falling into a pool, and the films Nicolas Cage appeared in any given year. Again, these aren't causal events. These are correlated events. There's something that says that they're strongly related, but there's no real explanation why. When we're dealing with statistics, we try and imply a causal relationship sometimes, but we need to remember that it's not necessarily the case. Cheese consumption and dying by becoming entangled in your bed sheets. Divorce rate in Maine and per capita consumption of margarine. Stay away from that margarine. It's a really fun site to explore. You're welcome to do that in your own time. Correlation does not equal causation. That's really important. Not just for in your maths, but when you're dealing with your other subjects as well. Second section, Pearson's product moment correlation coefficient. The R value. That's all it is. The correlation coefficient, the R value, when we're dealing with linear correlations. We've seen the coefficient of determination, R squared, which you would have used probably back in year 10 maybe when you were doing some PSMT work. But the R value telling us how closely things are related. There's the rule for it. You are not required to learn the rule. You just need to know how to use your calculator. So I have put the calculator instructions in there. We'll do an example in a minute so you can see. And the TI calculator instructions are there as well. If anyone has something other than the CG50, and this will work for the CG20 as well, or the TI-84, let me know and I'll see if I can find the instructions for those and put them in there as well. What does a correlation coefficient give us? It gives us a number between -1 and 1. The closer to either 1 or -1, the stronger the correlation. The closer to 0, the weaker the correlation. Positive value for R, positive correlation. Negative value for R, negative correlation. And you can see some good examples there. These are not strict definitions. Everyone will have a different idea of what definition they want to use for these, but these are pretty good to go with, and you can certainly use these when you're discussing your answers, and they'll be perfectly acceptable. Strong positive, 0.87 and above. If you want to call it very strong when it's over 0.95, that's up to you. Same with the negative values there. How do we come up with the line and this? We can find the correlation coefficient here. What we also want to do, of course, is to find the line of best fit. First way we can do it is just by drawing a line and trying to make it look right. In this particular case, they've suggested that you do it by finding the mean point first and then sketching in the value. So here they found the mean point, and the advice is draw a line through the mean point so that it follows the trend of the data, and there are about the same number of points above and below the line. You can argue whether or not you think that's perfect. It's up to you. Another way they often do it is they put it through, they use a median. They do the median of the first half of the data, median of the second half, and put it through there. That's another way you can do it. Line of best fit by eye is good for just getting a general idea of something. It's not fantastic in terms of giving us super accurate data. It depends on our purposes as to whether it's going to be suitable or not. Drawing a line of best fit by eye, it's going to be pretty easy for you to do. Find the average of the x-coordinates, average of the y-coordinates, put a dot there, and then have your line go through it. Quick note about interpolation and extrapolation. The lower pole and the upper pole, they're the extreme values of our data. When you're working in between those, it's called interpolation because you're between the poles. Extrapolation, extrapolation, outside the areas. In general, interpolation, we've got much more confidence about whether or not our prediction is true. Extrapolation, a lot harder to predict. Can't be as confident that we're going to be getting correct values using our rule outside those ranges. Here we've got an example. If you look at the opening problem in the book, they're looking at the age of people and the distance a discus is thrown. Someone who's 50, I'm getting closer. I'm unlikely to be throwing the discus 144 metres. Even though there was a nice strong correlation back here for people between the ages of 10 and 20, age had a big influence. I'm guessing after 20 it's going to flatten off pretty quickly, isn't it? Even if people train, it might go up for a little bit more, but it's going to flatten off. We're not expecting people at the age of 50 to be able to throw it 2.5 times as far as someone at the age of 20. That just doesn't make a lot of sense. So interpolation, I'd be pretty confident. Extrapolation, much less confident. So how did you calculate to get the line of best fit without just making it up, putting it through the median and hoping that's good enough? It uses what we call the least squares regression line. What it's doing is it's taking the distance between each x-coordinate and the y value for that x-coordinate and the predicted y value on the line that you're selecting. And then it's minimizing the sum of those distances. Now Excel can do this quite nicely, but there is actually a formula that will do it very well for us. What we're trying to do is minimize the squared differences, the sum of the squared differences. Of course we want to square them because we don't want the positives and negatives to cancel out. We're going to end up with the equation y equals ax plus b, where a is the sum of the product of each individual score minus the mean for the x-coordinate multiplied by the y-coordinate. And then we're dividing it by the sum of the x differences squared. And then the b, the number at the end, is the difference between the y mean and a, this entire thing, multiplied by the x mean. Why is that the rule? We don't need to know. That's good news for you. We just need to know how to do it on our calculator. But it might be interesting for you to try and read through that. Reading through mathematics is challenging, but if you can make sense of what they're doing, that's going to be helpful for you. It's good practice. Hopefully that will help. We don't want to read too much into data. We've already seen the spurious correlations. Anscombe's quartet here, these 4 particular graphs you'll see have the exact same mean, the exact variance in x. To 2 decimal places, the mean of y is the same. To 3 decimal places, plus or minus 0.003, the sample variance of the y values is the same. The correlation is correct to 3 decimal places, and they've all got a reasonably strong correlation, 0.81. The linear regression line is the same for each of them. And the coefficient of determination, the variation in the y value that can be explained by variation in the x value is 0.67. Clearly, these are not the same data set. We need to be careful whenever we're writing about this, and this goes for your IAs in other subjects, not just in maths. If ever you're talking about statistics, it's great to look at these properties. They usually give us a good indication, but you can't look at them in isolation. You need to look at the graphs of them as well, so you can actually compare and see whether or not, yeah, these are all related. They're probably very similar. They're clearly not very similar here. There are different things going on, and we need to be able to look at both the data and the graphs to get a better picture. The Datasaurus dozen is another one here. You can see there are 12 different sets. The mean of the x, the mean of the y values, the standard deviation of x and y is the same, and the correlation coefficient for each of these graphs is the same, yet they look remarkably different. So again, being able to look at your data in conjunction with the statistics you get from it is going to be really important there. You can explore those websites. I've left the links there so you can have a look at that. Interesting one that we probably haven't done before, the regression line of x against y. Usually we do y against x. We find y equals. Why would we want to find x equals something in terms of y? This is really interesting. What we're looking at is minimizing the horizontal distances rather than the vertical distances. When would we do this? Well, we do it when the precision in our measurement of the y values is more accurate than our precision in the measurement of the x values. There's a couple of examples here that I think explain it well. For instance, when a student studies for a test, the time spent studying explains their test score. They're correlated to a degree. It's not the only determining factor clearly, but there is a correlation there. The test score, however, is going to be much more precisely measured than the amount of time spent studying, even though there may be minor variations when I'm marking one paper to the next, in awarding a half mark here or there. It's going to be a much more precise measurement than students estimating how much time they studied and how effective that study time was. What proportion of the time they allocated to study did they actually study? So in that particular situation, actually doing an x versus y would be a better way of doing it. Another example, breath testing. A lot of you are getting your licenses now. Some of us already out there drinking. Use a breathalyzer to estimate the blood alcohol concentration of drivers. The result is sufficiently high, the driver has to take a blood test. The blood test result is a much more precise measurement. Yes, it's much more precise than the value you're going to get out of a breath test. So therefore we would want to minimize, we want to do x against y and minimize those y errors. It's basically the same formula with the x's and y's switched over, but you'll see here that the differences in the regression lines are quite interesting. Both of those regression lines are reasonable, but they're very different. Someone's trying to get me on the phone, but we're nearly done. We'll get through to the end of this. I want to do just one quick example using the calculator to make sure we're okay with how to do this. So let me exit out of that. So first thing I've done here is I've just put, well, we've gone off that page. Why did that minimize? Okay, we'll try that again. I'm not going to edit that out. You can cope. So we're doing this particular data here. Data below shows quantity of feed eaten by and the number of eggs laid in a fortnight for 12 leghorn chickens. Okay, clearly the number of eggs, we're going to be able to get a very accurate measurement on that, the number of eggs laid. We're not going to be as confident in our estimate of how much feed was consumed. Some might have spilt on the ground, some might have gone to waste or whatever. It's not easy to tell exactly how much food was consumed by each chicken. So therefore, we want to do the x against y. We want to do our correlation looking at we want to minimize the y differences rather than the x differences. When I put it into my calculator, excuse me, when I put it into my calculator here, and I've just got the data in there, I've just got the 12 values in there, hopefully I've got them right. If I exit out one, and we want to do, I'll exit right out so you can see, once I've put it in there, we want to do calculate, we want to calculate something, so that's F2, and we want to do a regression. When I go straight to my regression and X, because it's a linear regression that we're doing, and I want AX plus B, here I've got an R value of 0.99, excellent, very highly correlated. This is the equation of Y in terms of X. We want to turn it around and get X in terms of Y. You'll see my values in my screen don't match the values in the screen down here. How do I get it so that it turns it around for me? Because just transforming the equation won't give me the same line. what I do is I exit back out. And when I'm about to click regression, I want to go to my setup and just make sure I've got my setup right. In this particular case, I want to switch list 1 and list 2 around. I want to make the x values in the ax plus b actually my list of y values, which are in list 2. I want to make the y values in my y equals ax plus b that the calculator is going to give me actually the x values. So I change that to list 1. Now when I go out and do the regression, and do the linear regression, ax plus b, you can see here I'm getting the same values. The correlation is still 0.99. Correlation is still the same. The values are still the same. But now I've got, even though this says y equals ax plus b, you need to remember that it's x equals ay plus b. And there you've got the values. You can use this now to estimate values, answering those the part C questions there. You're just making substitutions in and rearranging the equation in the second case. So you're actually getting a formula for x instead of y. Why do we do that? When our precision in the measurement of the y value is greater. Alright, that's it for this chapter. It's a nice easy one to start us off. I think you'll be fine with the questions. If you've got calculator questions, give it a go. Hopefully that helps us. I will catch you in a video for the next section on discrete random variables. Bye for now.